Okay, today we're going to continue our stoichiometry problems, but this time we're going to add something to it. And what we're going to add to it, instead of doing a mass problem, we're going to do a mass volume. And what that means is we're going to start with a mass and end with a volume, or we're going to start with a volume and end with a mass. And these problems, I think, are actually easier just because of the fact that you do not have to come up with one of the molar masses, because for volume, you will always use 22.4. So just like a mass stoichiometry problem, the first thing we have to do is balance the equation. And again, I'm going to start with oxygen. On the left-hand side, the reactant side, I have 2 oxygens, so I need to put a 2. That gives me 4 coppers, so on the product side, I have to put a 4. And if you count, I have one carbon and 1 carbon on each side, and so that's a balanced equation. So the first question, letter A, asks us for the number of grams of copper produced if 400 cubic decimeters of carbon dioxide is also produced. All right. We are not starting with a mass. We're starting with a volume, 400 cubic decimeters. But that does not change our steps at all. We're still going to use the same 3 steps, or same 4 steps that we've been using. So we're going to start out with what we have, and we're going to put it over 1. And what we have is 400 cubic decimeters of CO2, carbon dioxide, and we're going to put it over 1. All right. Our second step has always been to take what we have and turn it into a mole. Well, because it's cubic decimeters or volume, and everything we're going to do is at STP, we don't have to come up with a molar mass. We're going to use 22.4. So on the bottom, we're going to say we have 22.4 cubic decimeters of CO2, and that's equal to 1 mole of CO2 on top. Cubic decimeters cross off. Now I have moles. My third step is always the same. It's a mole-to-mole ratio. All right, so moles of CO2 are on top, so moles of CO2 have to go on bottom. I'm going to put moles of what I'm looking for on top. And what I'm looking for at this point is copper, Cu. All right, one more time. Those numbers always come from the balanced equation. And from a balanced equation, I have 4 moles of Cu, and I have 1 mole of CO2. Moles cross off, moles cross off. My last step is to go from moles back to what I'm looking for. In this case, I'm looking for grams. So I'm going to go with 1 mole of copper on bottom. The molar mass of copper, the one we're going to use, is 63.5 on top. Moles cross off, moles cross off. And so I'm down to the mathematics part of it. So I have 400 divided by 22.4 times 4 times 63.5. And it comes out to 4,535.7. And that should be grams of Cu. That's our first problem. All right, second problem, a little bit more complicated. And I wouldn't do this to you on a test, but I would do this to you on an assessment or some kind of worksheet. And so the second problem is a little bit more difficult. This time we want to know the number of liters of CO2 produced when 2.5 pounds of Cu2O is used. And right away you ought to notice that it says pounds. And pounds, those are definitely an English unit. We're not going to use pounds. We're always going to use a metric unit. And so right below here I've given you a conversion that says 2.2 pounds is equal to a kilogram. Now when we think about molar mass, we never use kilograms for molar mass either. We always use grams. And so I think this is probably what we need to do. We need to go from pounds to kilograms, and then we'll change our kilograms to grams. All right, so we're going to start with the same thing we always do, what we have, and put it over 1. Even though it says pounds, we're still going to start with that. So we're going to start with 2.5 pounds, and that's a Cu2O, and we're going to put it over 1. This is where I use my conversion. My conversion says that 2.2 pounds, and those go on the bottom because they're on the top, is equal to 1 kilogram. All right, that got me from the English system into the metric system. All right, still don't want kilograms though. I want grams. And because we know that the prefix kilo means 1,000, then we can say in 1 kilogram, there is 1,000 grams. All right, so where I'm actually at right now, if you look at the units that are up there, I actually have grams of Cu2O. And I'm going to put parentheses around this, not because I have to do this first, but just kind of want you to see that this is all technically step number 1. So it took 3 steps to get step 1 done, but that's step 1 right there. So our step 2 is to take what we have and turn it into moles. Well, what we have are grams of Cu2O. So we have to take grams of Cu2O and turn them into moles. Well, if grams are on top, grams have to go on the bottom. And this step will always be 1 mole. So we have 1 mole of Cu2O on top. And we have to figure out the molar mass of that. Well, copper weighs 63.5. There's 2 of them, so that would be 127. Plus, we have 1 oxygen, that's 16, so the total would be 143. So our molar mass is 143. All right, the grams are going to cross off. I now have moles. Now, when I say about moles, if you remember your mole chart, once you're at moles, you can go anywhere you want to go. Well, we're going to do a mole-to-mole ratio here so I can get from one substance to another. So we're going to go with moles of Cu2O on bottom, and we're going to put our moles of what we're looking for, which is CO2, on top. Now, once again, those numbers, when we do our mole-to-mole ratio, come from a balanced equation. So from a balanced equation, I have 1 mole of CO2, and I have 2 moles of Cu2O. That takes care of that one and that one. Our last step is to go from mole back to what it is that we're looking for. And this time we're looking for liters. We're looking for a volume. So we're going to go with 1 mole of CO2 on bottom. And that's always going to be 22.4 because everything we do is going to be an STP. That crosses out my moles, and I now have liters of CO2, and it's a matter of taking care of the math. Now, once again, if it's on top, we multiply. If it's on bottom, we divide. So we start with our 2.5 divided by 2.2 times 1,000 divided by 143 divided by 2 times 22.4, and it comes out to 89.0 liters of CO2. That is a mass volume problem. And like I said, I think it's actually easier than a mass problem just because of the fact that one of the numbers you do not have to come up with. We'll always use 22.4. So we've just finished a mass volume problem. Hopefully that's helpful to you.